Hello, everyone. I'm Hong Yi Li, and today I'm going to talk about deep learning for speech processing. And we do not have a host today. I'm going to host this lecture myself. I'm an associate professor from National Taiwan University, and this is all I want you to know. And before we start this lecture, there's something I want to warn you. This lecture may be the most relaxed lecture in MLSS 2021 until now. We do not have any equation. We do not have any math in this lecture. If you want to learn something tough, I'm very sorry about that. There's nothing tough in this lecture. I'm only going to share with you some stories. So before I start this lecture, I want to let you know the main purpose of this lecture. I want to let you know that if you are familiar with sequence-to-sequence model, then you are ready to engage in speech technology. Because sometimes students come to me say, Professor Lee, I really want to do something related to speech technology, but what is the prerequisite? Do I have to be a linguistic before I study speech technology? Do I have to be very familiar with signal processing before I start to engage in speech technology? The answer is actually no. I want to let you know that if you are familiar with sequence-to-sequence model, I believe most of the audience are already familiar with that, then you are ready to engage in speech technology. Why? In speech technology, you can mainly categorize the model into 3 categories. The first class is you need a model which take speech as input and output text. And for the second category is text to speech, a model take text as input and output speech signal. For the third one is speech to speech, the model takes speech as input and output speech signal. And for both speech and text, they can both be represented as sequence. So all the 3 kinds of model can be modeled by sequence-to-sequence network. And for example, you can use transformer, and you can ask the transformer to take speech as input, output text as input, output speech as input, output speech. Then that's it. This is all you need to know to work on these 3 types of model. So sequence-to-sequence model or transformer is all you need. I hope I already convinced you that if you are familiar with sequence-to-sequence model, you are ready to engage in speech technology. So this is all I mainly want to share with you. Thank you very much for your attention. It looks like we have probably 2 hours for question and answer. Let me check whether there's some question in the chat room. Unfortunately, there's no question. Until now, you still do not have any questions. So we leave 2 hours. I allocate myself 2 hours. So it looks like I have to share with you something more. So probably besides that you know that sequence-to-sequence model is good enough, I can probably also let you know that besides sequence-to-sequence model, if you want to be the top in the field, you need to understand something more than sequence-to-sequence model. Let me share more about those 3 categories of model with you. So for the first category, input speech signal, output text, input speech signal, output text, this is actually speech recognition. I believe all of you are already very familiar with speech recognition technology. And here I want to share with you some history about speech recognition. Actually, speech recognition is nothing new. Before 1960s, the researchers have started working on speech recognition. However, in 1960s, people believe speech recognition is very difficult. In 1969, J.R. Pierce wrote an article. The title is Whether Speech Recognition. Who is J.R. Pierce? J.R. Pierce is the one who led a team invent transistor. So usually he's considered as the father of transistor. So he's a very important guy in build that. Then he wrote an article. This article criticized the research about speech recognition. He thinks speech recognition is something just attract money. It's too challenging. We are too far away from general purpose speech recognition. He considered working on speech recognition is just like turning water into gasoline, extracting gold from the sea, curing cancer, going to the moon. So all those tasks are very challenging even today, and JR Peers consider speech recognition is as challenging as those tasks. And unfortunately, I heard that after Bell Lab read this article, they stopped the funding of speech recognition. But today, speech recognition is not sci-fi anymore. As you know, there are tons of virtual assistants around you, and those virtual assistants, they can all recognize speech. So recognize speech is nothing new. So before we begin to talk about the technology, let me share with you one more story to show you how popular speech recognition system is. See, speech recognition system is truly everywhere. So in 2017, a 6-year-old girl living in Texas asked her Amazon Echo, say, can you play dollhouse with me and get me a dollhouse? As you can expect, Echo buy a dollhouse for the 6-year-old girl. But this is not the end of the story. Tomorrow in the morning news, the anchor say, I love the little girl saying, Alexa, order me a dollhouse. Then all the Alexa in the US try to order a dollhouse. The TV station obtained so many complaints from the people. But this is also not the end of the story. So after a few months, Burger King, they have a new idea about advertisement. This is the new ad of Burger King.
You're watching a 15-second Burger King ad, which is unfortunately not enough time to explain all the fresh ingredients in the Whopper sandwich. But I got an idea. Okay, Google, what is the Whopper burger?
Okay, so this is the Burger King's new idea about how to advertise Whopper burger. And how can Google Home know what are the ingredients in Whopper burger? This is because Google Home will search the Wikipedia. So you can imagine that someone probably from Burger King changed the Wikipedia webpage about Whopper before the ad is broadcast. So originally, the wiki page of Whopper is very normal. It's just humble. Then before the ad is broadcast, someone named Fermentido123 modified this wiki page, and it tried to write something good about Whopper. It tried to introduce the Whopper burger, and this is the username of Burger King's marketing sheet. But as you know, everyone can modify the wiki page. So lots of trolls try to modify the wiki page after the ad is broadcast. So I try to check the editing record around that period, and you can find that the wiki page change every minute. So someone say Whopper is made by 100% medium-sized child. Someone say Whopper is made with 100% red and toenail clipping. And someone even say it remains far inferior to Big Mac. So this story is not intention to hurting or opposing any company or individual. I just want to share with you how popular those virtual assistant is. You can even use them to do the advertisement. So let's start to talk about technology. Before I start to talk about technology, I found that there's a question in the chat room. Let me check the question. Okay. There's a question. Is there any way to convert audio speech signal to spectrogram using DNN? There are many ways to do it, but for some reason, I need it. If it's learnable, making it simple, can we convert audio signal to spectrogram using convolution layer or block. Okay, this guy wants to ask how to transform speech signal into spectrogram. We will talk about that later. Okay. Okay, so let's start to talk about technology. So what we want to do is speech recognition here. The input is speech signal, the output is text. And as I have mentioned, both speech signal and text can be represented as sequences. So speech is a sequence, text is another sequence, and these two sequences may have different length. It is very possible that their length is very different. Usually the input sequence here is much longer than the output sequence. So the sequence of speech is much longer than text. Then before we talk about the model here, but before I talk about the model, you can already imagine that it's a sequence to sequence model. You can use transformer here. But before we talk about the model, let me introduce how to transform the speech signal into a sequence of vector or a sentence into a sequence. So let's start from text. How to represent text as a vector sequence. So this is a sentence. Given a sentence, you will first do the segmentation. You will segment the sentence into a sequence of tokens. In the example here, the length of this sequence is 5. So capital N, the length of the sequence is 5. And there are 3 different tokens. I use different color to represent different types of token. I use different color to represent different token. And there are A, B, 3 different tokens. This is very simple. However, what is token here? So what is the token here? There are many different ways to define what is token. For English, a very intuitive way is consider word as token. So for a sentence, One Punch Man, it can be separated into 3 tokens. Each word separated by the space is 1 token. But the problem here is if we consider word as token, in English, the number of token will be very, very large. It's probably larger than 100,000 or even larger. And as you know, new words are always invented. So the number of different tokens are always increased in English. And another problem is that for some languages, the word boundaries are unclear. For example, in Chinese, there's no space to separate the word. So the word boundary is unclear. So it's not that easy to define what is word in Chinese. And another choice is morpheme. What is morpheme? Morpheme is the smallest meaningful unit. It's something smaller than word. For example, in the word unbreakable, un and break and able, they are morpheme. They have meaning, but there's not a word. You can compose several morpheme together to form a word. So you can compose some morpheme to even create the word probably not exist in the dictionary. For example, you compose re and kill and able, you have rekillable. Probably, I'm not sure whether there's a word rekillable in the dictionary, but you can guess the meaning by those morphemes. So rekillable is probably someone like Kenny. You can die and live again several times. But what are morphemes in a language? This is also a difficult question. There are 2 ways to obtain morpheme. One is you need some linguists to help you. Another possibility is based on the statistic. You go through all the words in the dictionary and find what is the most frequent patterns in the word, and probably those patterns can be considered as morpheme. Actually, in the lecture today, in the lecture this morning, Dr. Zhang has mentioned word piece several times. Word piece can be considered as one kind of morpheme. Besides word and morpheme, in speech recognition, the most widely used token is probably grapheme. So you usually hear some people use grapheme as their output of speech recognition system. And what is grapheme? Grapheme is the smallest unit of a writing system. In English, it's the alphabet. So there are 26 English alphabets, so there are 26 morphemes. for English. So given a sentence one punch man, if you want to segment this sentence into tokens based on graphing, then the first token is O, the second one is N, the third one is E, then the fourth one would be the space. You need to consider the space also include in your morpheme, or you will not know the boundary of the word. So space is also considered in the morpheme. Or if you want to consider punctuation marks, you also have to include punctuation marks in your morphemes. So the number of different morphemes is larger than 26. Another widely used token is phoneme. So morpheme is the smallest unit of a writing system. Phoneme is the unit of sound. So to use phoneme, you need a lexicon. In the lexicon, you have the mapping from word to phonemes. So you have the mapping from word to phonemes. Given the sentence to represent into a phoneme sequence, you have to look up the lexicon. Then you can find the phoneme of each word. Then you can transform a sentence into a phoneme sequence. Phoneme sequence is also widely used in speech recognition because phoneme is the unit of sound, so it is very highly correlated with speech. So if you use phoneme as the output of the speech recognition system, this will make your model simpler because your output is highly related to your input. However, the problem of using phoneme is you need a lexicon here. If a word is not in the lexicon, this is called out of vocabulary or OOV, then you do not know the phoneme sequence of this word. You need other way to try to guess the phoneme sequence of the word. And graphing is lexicon free. This is the benefit of graphing. So what is the most popular token in speech recognition? Actually, my students and I go through more than 100 papers in interspeech, ICASP, and ASIU 2019. We go through all the speech recognition papers in this 3 conferences. These 3 conferences are the top 3 conferences in the speech community. And we found that graphing is the most popular unit for speech recognition. And the second one is phoneme. Some people also try to use morpheme, and the word is the last choice. But besides these 4 kinds of token, there's other way to define your token. Probably you say, I don't want to know anything about language. I'm not a linguist. I do not want to know what is graphing, what is phoneme. Then fine. There's a very universal way to define your token. If you know nothing about the language, you can simply consider bytes as your token. You know, every sentence can be encoded by UTF-8 encoding. So given a sentence with UTF-8 encoding, you can transform it into a byte sequence. And this way is very language independent. You do not need to know anything about language. Given any language, you can transform it into a byte sequence. And so you can transform any sentence from any language into a token sequence. And in this example, if we use bytes as our token, how many different tokens do we have here? This is a question to you. Let's try to do some interaction. How many different tokens do we have if we use bytes as the definition of token? What is the number of different tokens? What is the D here? You can type your answer in your chat room. Actually, I can see the chat room at this moment. So please type your answer about how many different tokens do we have in this example in the chat room. I know there's some lag between what I actually say and what you actually heard. So probably I have to wait for a while. Okay, lots of people say 256. Yes, 256 is the correct answer. So it looks like we are at the same page. You know what I'm talking about. Good. Then the next question is how to represent speech as a vector sequence. So this is speech signal. if we look closer and closer, speech signal is actually a sequence of numbers. So as you know, speech signal is waveform, but if you look at the speech signal closer and closer, it's a sequence of numbers. Because speech signal is a sequence of numbers, it is very natural to represent as a sequence. So you can just say this speech signal is a very, very long vector sequence. Each vector only has one value. Each vector only has one dimension. However, if we use this way to represent speech, then your sequence will be too lengthy, because in speech recognition, usually the sampling rate is 16K Hertz. That is, in 1 second, we have 16,000 sample points. And if 1 second of speech have to be represented as 16,000 sample points, then the sequence, then given an utterance, this sequence will be extremely long. And as you know, if we use something like self-attention or LSTM to process a very long sequence, this will cause a lot of problems. So how to make this sequence shorter? So in speech recognition, usually we do not directly take this sample as a vector. We do not directly represent those samples as a very, very long sequence. What we actually do is we will extract something called acoustic feature. So you will first have a window. You will take a window from your utterance, and this window, the size of the window is defined by yourself, but usually people will choose 25 milliseconds. So, and this window is called a frame. And you will use one vector to represent each frame. So each frame corresponding to one vector, and this vector is called acoustic feature. And there are many different ways to represent the acoustic feature. The most naive way is you just take all the samples here. You concatenate all the samples in this window, in this frame, as the acoustic feature. If your sampling rate is 16,000 and there are 400 samples in 25 milliseconds, then this vector will be 400 dimensions. But this is not the best way. There are other ways to represent the acoustic feature. The most widely used approach, probably before 10 years before, is NFCC. And today, the most popular way to represent a frame, the most popular acoustic feature is probably filter bank output. So there are many different ways to represent a frame. There are many different kinds of acoustic features. If you do not know what is NFCC or filter bank output, it's fine. Don't worry about it. Just consider it as some handcrafted features. And this is just one frame. You use one vector to represent one frame, and an utterance is much longer than 25 milliseconds. So you need multiple frames. And there will be some overlap between frames. Usually you only shift a frame by 10 milliseconds. So there is some overlap between frames. And here is a question for you. Type your answer in the chat room. If we have speech signal, which is 1 second, then how many frames will we have based on the definition here? And just choose the answer which is most close to the correct answer. Just choose an approximate number, ignore the condition information, ignore the boundary information. Which number do you think is most close to the correct answer? Here is A, B, or C. Type your answer in the chat room. Let me see whether we are on the same page. I know I have to wait for a few seconds before you type the answer. Okay, most people think it's B, so it looks like you understand what I'm talking about. That's great. Okay, so I have one page to tell you how to extract those acoustic features. So you have waveform here, then you will do a transform called DFT. Don't worry if you do not know what is DFT, then you get spectrogram. And I know there's a student asked how to extract the spectrogram. I have to tell you that usually you do not need deep network to extract the spectrogram, because from the waveform to the spectrogram, you only need an operation, and this operation, EFT, is the linear transform. And there's lots of model package there's lots of Python package can already do that for you. So usually you do not really need the network here. You can use librosa or you can use PyTorch Audio. Both of them are pretty widely used Python package. They can extract the spectrogram for you. So even though you do not know why SteveFT, don't worry about it. Just call those package and they will give you spectrogram. They will transform the waveform into spectrogram. But spectrogram is not the most widely used acoustic feature. You will pass the spectrogram through a set of filter banks. So you obtain the filter bank output, and probably you will take log and take DCT. Don't worry about what is DCT, then you obtain NFCC. And those stages can be performed by just a command line in those packages. So don't worry about what is DFT or what is DCT here. So why we have this process to obtain the acoustic feature? Actually, this process is trying to mimic the auditory system. It tries to mimic what your cochlear work. I'm not going to go through the detail here. I just want to know that those processes, the filter bank, they are not come from nowhere. They are come from your auditory system. So what is the most popular acoustic feature? So we go through the papers in 2019. Then we found that in 2019, the most popular feature is actually filter bank output. The second one is NFCC. Only 18% of the papers use NFCC, and there are only little paper use spectrogram or waveform. So this shows that actually you will not directly use spectrogram as the input of your speech recognition system. Most paper, they are more than 75% of paper actually choose filter bank output. I found that there are some questions in the chat room. Let me check it. Oh, a student asked, is there any overlap between two consecutive windows? Yes, I have already mentioned that, but this is a very good question. Yes, there should be overlap. Okay, a question here is, it seems like the different tokenization methods mainly different by their level of granularity, with UTF-8 being the most general and graphing being the second. So which one to use is determined by how much data you have. Does this summarize the current zone of tokenization methods? This is also a very good question. So I think you have a very good sense that which token you choose depends on your task. Actually, using the UTF-8 is not the most widely used approach, because usually, given you a language, you already have some general idea about the language. So the most frequently used tokenization approach in speech recognition is actually graphing. And because we have enough data, graphing is actually a very small level of granularity compared with word piece or a word. So if you use graphing as your token, it is possible that your speech recognition system will have the wrong spelling. For a user, probably it's very hard to believe that speech recognition system will have the incorrect spelling. But if you use graphing as the granularity, wrong spelling is possible. But fortunately, if you have large enough of data set, if you have sufficient data, graphing is usually good enough. Machine can learn the lexicon itself. It will not frequently spell 的 word wrong. Okay, so let's go back to the acoustic feature here. So it looks like filter bank is the most popular one. And there's two very interesting facts I want to share with you. The first is 10 years before, when I was a student, NFCC is the most popular one. At that time, no one used filter bank. All the paper used NFCC. And in 2014, deep learning started to become very popular in speech community. And at that time, Dandy is he was at Microsoft at that time, and he's the pioneer of deep learning in speech community. And then they give a keynote at Interspeech 2014. And at that time, he predicted that NFCC will disappear because he thinks there are many different stages in feature extraction, and probably deep network can replace some stages in acoustic feature extraction. So NFCC will disappear one day. Is it true? Based on the statistic of 2019, it looks like this is pretty close. So now the last stage of NFCC is removed. We do not do DCT anymore. We can directly use filter bank output. However, there's another interesting fact. You can find that there's only very little people using waveform or spectrogram. Most of the speech recognition system still choose to use filter bank output. So it's different from image processing. I know in image processing, most of the image recognition system today, they can directly take pixel as input, but in speech recognition, waveform is not widely chosen. You can use, of course, some systems try to use waveform as their input, but it's very hard to get the same performance as filter bank output. So this shows that those filter bank are still very important. Something you get from the auditory system, this kind of domain knowledge is still very important. This should tell us one thing, even though we already have a very deep network, those domain knowledge is still very important. I found a question here. Okay, some people say, I wonder what is the other in acoustic feature. I do not remember its name exactly. It's a new kind of feature. I think it's invented by Berkeley. They have a new type of acoustic feature in 2019. Oh, this is a good question. Someone asked. One more question is the spectrogram here in log male scale. When we do, okay, this is a very good question. When we go through the paper, we do not especially check is log male scale or not. So sorry about that. I think I cannot answer your question at this moment. But even though you choose to use log male scale, I think filter bank output still can outperform spectrogram. Okay, so before we talk about the technology, this is another statistic to show you how large the data set we need to train the speech recognition system. So here I list some of the well-known corpora. The smallest one is timid. Timid can be considered as the NIST of speech recognition. So if you have some new idea, usually you implement your new idea on timid. It's 4 hours. And there's of course some larger corpus. Libre speech, which is 960 hours, is the most widely used corpus today. And I want to compare the size of this speech corpus with the image benchmark corpus. How to compare that? You can try to compare the size of those different corpus. You can try to transform your images into the audio with the equivalent size. That is, for example, in NIST, you have 16,000 images, and the resolution of image is 28 times 28. So you have approximately 47 millions of numbers in the NS corpus. And if you consider you have audio with 16,000 hertz, then 47 millions of number will be 49 minutes. So you can say NS is equivalent to the size of 49 minutes of audio corpus. For Cipher 10, do the same calculation, can be equivalent to 2 hours and 14 minutes. So both NS and Cipher 10, they are actually smaller than 10 minutes. And for ImageNet, ISLVRC is around 4,000 hours. But today, if you want to build a really good speech recognition system, you need much larger corpus. In the paper of Google or Facebook, usually they tell you that they use the corpus larger than 10,000 hours to train their model. But actually, the researchers from Facebook and Google, they always tell us that they do not show the real number in the paper. In their commercial system, usually they use data probably 10 or 20 times larger than what they say in the paper they published. So let's talk about the models. So we also go through the paper in 2019 to see which model is most popular in speech recognition. So you can find that the most popular one is LAS, and the second is CTC, and the third one is LAS plus CTC. The fourth one is RNNT, or actually the third one is HNN hybrid, and the fourth one is LAS plus CTC, and the last one is RNNT. And for HNN hybrid, it's actually not an. And I think we have a question here. The question is, do you have any idea why the filter bank output become the most popular one? The answer is very simple, because it obtained the best performance based on today's model. So it became the most popular one. But I give you this statistic because I want to show you that filter bank is the most popular one. That means filter bank, they are still very important. Those filter bands are designed based on your auditory system. So those domain information is still very useful even in the era of deep learning. Okay, so I want to talk a little bit about HNN hybrid. So HNN hybrid is not an end-to-end model. It is one kind of, it try to modify the original speech recognition system. In the original speech recognition system, you have several modules. You have acoustic models, you have lexicon, and you have language model. In the hybrid model, the acoustic model is replaced by deep network. And actually, they also still maintain the hidden Markov model in the acoustic model. They use deep network for emission probability and use HNN for transition probability. Don't worry if you do not know what I'm talking about. You just have to keep in mind that for hybrid model, it's still deep learning based, but there are several modules in your speech recognition system, so they are actually not end-to-end. So what is LAS? It is nothing special. LAS is listen, attend, and spell. It has a fancy name here, but actually it's just the typical sequence-to-sequence model with attention. Listen means encoder. Attend is attention. I do not have to describe what is attention for you. Spell is the decoder. So the most popular model in speech recognition, LAS, is just sequence-to-sequence model. So does it work? As you know, sequence-to-sequence model has been invented in 2015. The first time I read the paper of sequence-to-sequence model, it is originally invented for machine translation. The first thought come out of my mind is it can be used in speech recognition, because speech recognition can also be considered as sequence-to-sequence model. But I never tried it because I think speech signal is more sophisticated than languages. In machine translation, the input is a sentence. You can use sequence-to-sequence model to process it However, in speech recognition, the input is occlusive feature is usually much longer than a sentence. So it's usually very, very long. So probably we cannot use an AINTU model to deal with it. However, then next year, some people try to apply sequence-to-sequence model on timid. When you have a new idea, you always try timid first. Then they found that they get an error rate, which is 17.6%, which is pretty good on the timid benchmark corpus, which is very close to the SOTA at that time. So, however, even if a model works on timid, doesn't mean it works on other models. In the speech community, there are always tons of models that can work on timid, but cannot scale well on the larger corpus. So even though in 2015, I already see the result of sequence-to-sequence model on timid, I still do not believe sequence-to-sequence model can work well on speech recognition. In the same year, I read a paper in interspeech, and in that paper, they try to extend sequence-to-sequence model on a larger corpus, which is switchboard. Switchboard is 300-hour corpus. Then they get error rate, which is 38.8. Is this a good error rate? You need a baseline, right? So on switchboard, what is the baseline? In the paper last year, which is not an end-to-end model, they already achieved 10.4% error rate on the same corpus. So it looks like 38.8% error rate is pretty poor. So at that time, in 2015, I still didn't believe LAS sequence-to-sequence model can work well on speech recognition. However, things changed. In 2016, Google used 20,000 hours of data to train a sequence-to-sequence model to train the LAS here. Then they get 16% error rate on their corpus. And actually, their performance is not SOTA is not state-of-the-art on their in-house corpus because their hybrid model can get much better performance than the sequence-to-sequence model. However, their result tells us that sequence-to-sequence model has the potential. It is already not far away from the traditional hybrid model. Then in 2018, Google tried to use 12,000 hours of data to train a sequence-to-sequence model. Proposed here is a sequence-to-sequence model that eventually they get better performance than conventional hybrid model. And they also want to tell us that the sequence-to-sequence model is more compact than the traditional model. In the traditional model, there are several modules. You have acoustic model, you have pronunciation model, you have language model. Put all the model together, then your model will be pretty large. However, sequence-to-sequence model is more compact. You just have a neural network, and it will take the role of all the different modules, put all the different modules in the same network, and it is smaller than the traditional model. Okay, so I think there is some question. The question here that in the ASR system, is that possible to combine several features as the input to train the system? Would it have any advantage if we are do so? Yes, I actually combine different features is widely used, especially before the age of deep learning. In the age of deep learning, people do not care about the acoustic feature as much as before. People more care about the neural network. But before, in speech community, before people started working on deep learning, lots of people working on this kind of feature engineering. So there are tons of new acoustic feature proposed every year. And what usually people do is when you invent a new acoustic feature, usually it did not really perform well. So a very widely considered approach is concatenate your proposed feature with the NFCC, because NFCC is too powerful. It is so good before people start to use deep learning. So usually you concatenate your invented feature with NFCC, then you write in the paper, say after the concatenation, we still get some improvements so you can get your paper accepted. So combine several features is widely considered before, but today feature is not as important as before. I hope this answers your question. Okay, so let me skip a few pages. Besides speech recognition, sequence-to-sequence model can do more than that. Sequence-to-sequence model has been successfully applied on speech translation. That is, the input of the model is the utterance of one language, and the output is the text of another language. The content in the utterance and the output sentence, they have the same meaning, but the input language and the output language can be completely different. That is, you do speech recognition and translation at the same time. You do speech recognition and the translation in the same model. And besides that, you can put speech recognition and intent classification together. You can say you have a model, the input is the utterance, and you do not do speech recognition, you do not output speech recognition result, you directly output the result of intent classification. And you can also do more than that. You can say you train a model, do speech recognition, and slot feeding at the same time. So the input is the sentence, is an utterance, and the model can directly output the result of spoken language understanding. It directly output the result of slot feeding. So sequence-to-sequence model can do something even beyond speech recognition. And here is a comparison between the hybrid model and the end-to-end model. Actually, you can find that to surpass hybrid model is actually very struggle. When you only have very little data, you only have hundreds of hours of data, train an end-to-end model may not be as good as the hybrid model. So hybrid model need less data. If you want your end-to-end model to be as good or even better than hybrid model, usually you need more data to train your end-to-end model. And there's some benefit for hybrid model. It's very easy to add new token into the hybrid model. You only have to modify your lexicon. But for end-to-end model, it's kind of tricky to add new token. You need to invent some new approach to add the new token directly. This is still something under investigation. And there's one interesting aspect people do not every people know. For hybrid model, it's easy for teamwork. In hybrid model, you have different modules. So in a big company, you will have different group of people working on different module. Someone working on acoustic model, someone working on language model, someone working on lexicon, and put them together, then you have a good speech recognition system. Then for end-to-end model, it's kind of hard to collaborate because there's just one model. How can different teams collaborate? And however, there's some benefit of the end-to-end model. As I just told you, hybrid model is larger, end-to-end model is more compact. And hybrid model is relatively difficult to implement. An end-to-end model, you can easily implement it by PyTorch or other deep learning framework because intrinsically just an end-to-end model is just a sequence-to-sequence model. And I have to tell you the truth that most commercial systems are based on hybrid model. However, if you want to write a paper about speech recognition, end-to-end is what you need because you can find that in 2019, most of the papers are based on the end-to-end model, not hybrid model. So this is some comparison between hybrid model and end-to-end model. And LAS, this kind of end-to-end model, sequence-to-sequence model, is not the answer of speech recognition. Why? Because if you use a sequence-to-sequence model, you cannot do online speech recognition. Because in sequence-to-sequence model, the encoder first listens to the whole utterance, then the decoder starts to decode the token. And you cannot do streaming in this way because if your encoder do not listen to the whole utterance, your decoder cannot start to decode something. To achieve online speech recognition, that is when the utterance is input, you do the decoding at the same time. LAS is not what you need. So LAS has some limitation. Sequence-to-sequence model has some limitation. It is not the final solution of speech recognition. You need other model to deal with the problem of online speech recognition. So you can imagine that if you want to use LAS in your cell phone, it is not appropriate because usually people expect online speech recognition. That is when you start to say something, your models output some text at the same time. And this cannot be achieved by LAS. So what kind of model can achieve online speech recognition? CTC may be a good choice. So the second popular model is CTC. CTC is connection-less temporal classification. I see a question in the chat room. For more than speech recognition, are the tasks trained end-to-end without splitting the two tasks? Yes. If so, why isn't it better? If so, why isn't it better to introduce some auxiliary laws for the intermediate task? Since usually you still have label for both tasks. Okay, this is a very good point. For some languages, they do not have writing system. Actually, around 50% of the languages do not have the writing system. This is why this kind of end-to-end fashion is attractive, because you can deal with those languages without any text, without the writing system. However, for the language with the writing system, you can have the auxiliary laws. Actually, for speech translation task, to achieve the state-of-the-art result, auxiliary test is needed. That is, you have an encoder, and the input is speech signal of English, and your output target is Chinese character. However, you also have another decoder try to decode the English sentence based on the output of the encoder. This is a very widely used approach. There's another question. Oh, okay, this is the continual of the last one. For example, for speech recognition plus translation, we still have the English plus Chinese version. How is the issue of fairness deal with this model? Of course, other than getting how is the issue of fairness deal with this model? Of course, other than getting a more balanced data. So it looks like this is a separate question. The question is about the fairness issue. This is a very good question. In the speech community, there's not too much research about fairness until now. So I also have this question. So if we train a speech recognition system, if we have some unbalanced data, for example, the female data is more than male, then what would happen? How large influence would it be? There's not too much research until this time. This will be a very good research topic if you are interested in speech technology. So let's talk about CTC. Okay. So in CTC, we want to get rid of the decoder. We only have the encoder. Of course, your encoder should be unidirectional. You cannot use bidirectional LSTM, or you cannot do streaming. You cannot do online speech recognition. To do online speech recognition, this encoder have to be unidirectional. So input X1, it can directly output H1, input X2, output H2, input X3, output H3, and so on. Then we do not need a decoder. We simply take a classifier. The classifier take this H as input and output the token distribution. The classifier try to directly determine this small segment, this frame, belong to which token. However, if you directly use this strategy, there will be some issue. If you just use a classifier to try to classify each vector here belong to each token, then there's an issue. Let's consider an example that we have 9 acoustic features here. If we have 9 acoustic features without a decoder, the output will be exactly the same length as the input acoustic feature. So input 9 acoustic feature, the now output will be 9 tokens. Let's say the output is N, N, L, L, and 5 consecutive S. If this is the output, you cannot interpret its MLSS or NLS. You do not know these 5 consecutive S represent 2 S or just 1 S. So in CTC, we use a very smart way to deal with this problem. It adds an extra token into your token set. So if your token set is all the English alphabet, CTC will add 1 more token. This token represents null. This token represents the separation between the output token. So for CTC, its output will include this kind of null symbol. So if the output of CTC is something like N, N, null, L, L, null, null, S, S, then this is NLS. You remove the null and you merge the consecutive token. So this 2S will be considered as 1. If your output is like this, S, null, null, S, the null is considered as the separation between the different tokens. So if your output is S, null, null, S, then it will be MLSS. So CTC use the null to separate the tokens so you can deal with this ambiguous issue. However, when you try to train, I think we have more questions here. Oh, no, we do. No, we do not have more questions here. However, to train CTC, there is an issue. Because as you know, all the classifier here need a ground truth. Here we input 4 acoustic features, then you need the ground truth for each acoustic feature. However, in speech recognition, your label is usually like this. So you have acoustic feature sequence, you have token sequence. However, the length of the token sequence is much shorter than your acoustic feature. In this example, there are 4 acoustic features, but you only have 2 tokens. Then how can we know the 4 ground truth here should be H or I? So we do not know that we should say the first acoustic feature is H, the rest 3 is I, or the first 2 is H, the rest 2 is I, the first 3 is H, the last 1 is I, and so on. We do not know which one is correct. To deal with this problem, this is how CTC do. They are all kinds of different arrangement between the input acoustic feature and the output token. For example, you can say the first 2 acoustic feature corresponding to H, and the third one is null, and the last one is I. Or you can say the first one is H, the rest 3 is I, and so on. There are many different kinds of alignment between the acoustic feature and the token sequence. Which one is correct? CTC do not care about it. In the original paper of CTC, they consider all the possible alignment as the correct one. They train their model with all the possible alignment. You may be very surprised if this is the first time you heard this technology. How can we enumerate all the alignment and use all the alignment during the training? This is based on some special algorithm. Actually, it's not very special. It's just dynamic programming, but I'm not going to go through the detail here. I encourage you to check the paper yourself. I put all the reference in the last few slides of this talk. I found that there is some question, okay? The question here is, how did CTC know when to output a null? So this is an excellent question. CTC learn by itself. It has to decide when to output the null to obtain the correct answer. So when to output the null is learned from data. CTC is actually kind of sophisticated. It's hard to go through the detail today. If you want to know all the detail, you can check the paper yourself. Okay, here is a question. Considering both forward and backward makes sense in video, does that make sense in speech and text in the training set? I do not sorry, I do not really get this question. Consider both forward and backward make sense in video. Instead make sense in speech and text in the training set. It looks like the question is not finished yet. Probably you can reformulate your question. Okay, so while we are waiting for the people typing, we continue to talk about CTC. This is the actual output of the CTC model. Based on the previous example, I probably give you a wrong impression that null is just happen between the two phonemes. But actually, this is not the strategy of CTC. If you truly train a CTC model, its strategy is more like this way. If, for example, in this utterance, it first output H, then it output lots of null. The dotted line here represent null. Then it output I, a null, and S. This is represent space. Then output a very long consecutive of nulls. Then output F, some null, R and I, a lot of null. So null is actually the most frequent token the CTC model output. CTC model usually output null. It usually just output the token English alphabet once when it truly listen through the whole token. So this utterance would be his friends. Okay, here we have the question. Why can be used bidirectional LSTM in speech recognition? Because I have used several times for OCR such model. You can use bidirectional LSTM. I mean, in lots of paper, you use bidirectional model in speech recognition. However, in the real implementation, if you want to build a conversion system, usually you want your system to build streaming. That is, if your model is bidirectional, your customer have to wait he or she say the whole sentences, then the model will output something. However, when you use your cell phone, when you use Siri, you found that before you finish the whole sentences, the model already outputs something. So you know the model is listen to what you are talking about. Because if you wait too long, you will not have the patience. You want the model to output something while it is listening. To achieve output something while listening, to achieve online speech recognition, you cannot use bidirectional models. I hope this answers your question. Okay, so, okay, there's no more question. So this is CTC model. Then the third one is LAS plus CTC. Due to time limitation, I think I have to skip this one, but the idea is very simple. Just put the two models together. And RNNT or RNN transducer is another very important model because it is actually used in Pixel 4. RNNT is the model really used in the commercial system. So when you do speech recognition on Pixel 4 in the offline scenario, your Pixel 4 actually use RNN transducer. So this is a very important model, but it is even more sophisticated than CTC. So we do not have time to go through this model today. I just want to let you know that RNN transducer is the model that is used in the commercial system. Okay, there are more different models you can study. I leave the reference here for your consideration. But this is not the whole story. This is just a part of the story about speech recognition, because in speech, there are many different information. Besides what is talking about, we also have to consider who is speaking. We also have to consider how the utterance is generated. So what is speaking means the content, who is speaking means the speaker, and how is speaking means something like quality or emotion or how you express what you want to talk about. So in speech recognition, you just extract the content information from the speech. However, there's also other application to extract the speaker information. or extract information other than content and speaker. We do not have time to talk about that. We will have a panelist to talk about more speech application in the last day of MLSS. Okay, I think due to time limitation, probably we still take a very, very short break here. We take a 5 minutes break, and you can leave your question in the chat room, use this chat. Okay, welcome back. I need to skip a few slides here. Those material will be talked about on Thursday, and the panelists in the last day. So we can skip a few slides here, but you do not miss anything because we will go back to them in the following lectures. We have a question here. Oh, here we have a very good question, but I do not know the answer. Can you come? Sorry, I do not see the question. Okay, the question here. Can you comment why it is much more popular to use EFT in speech recognition instead of other powerful methods such as Hilbert-Huang transform? I know Hilbert-Huang transform, but I don't know why people do not try it on speech recognition. But if you are familiar with Hilbert-Huang transform, you can try that to see whether it is helpful in speech recognition. Sorry, I do not have the answer at this moment. Do you know, the question is, do you mean that we don't have to master language or linguistics, but statistics at the early slide is about the statistic of the popularity of the techniques people used? Yes. So what I want to share with you is, even though you are not the master of language, but you know lots of things about statistics, you are familiar with machine learning, you can start to working on speech technology. Because you can find that in the paper I shared with you, most of the model, they are just end-to-end. They are just training a deep neural network. So this is all about speech recognition. For the next topic, I'm going to talk about speech synthesis. So we have a model, take text as input and output speech signal. This is speech synthesis. And speech synthesis has a very long history. Even in 1930s, people already working on speech synthesis. But at that time, in 1930s, speech synthesis is kind of like play piano. What do you mean? You can watch this video, you know what I mean.
The machine uses only two sounds produced electrically. One of these represents the breath. The other, the vibration of the vocal cords. There are no phonograph records or anything of that sort. Only electrical circuits such as are used in telephone practice. Let's see how you put expression into a sentence. Say, she saw me, with no expression. She saw me. Now say it in answer to these questions. Who saw you? She saw me. Whom did she see? She saw me. Did she see you or hear you? She saw me.
Okay, so you know that in the ancient time, when you do speech synthesis, it's like playing a piano. I would like to skip this one. And before people start to use end-to-end approach, there's some very popular approach. One of the most popular approach for speech synthesis is concatenative approach. That is, you have a very large database, you ask someone to read lots of sentences, and you segment those sentences into very small segments. And when you want to synthesize an utterance, you just pick some segments in your database, concatenate them together, then you have a complete utterance. How to select the proper segment is the core of this technology. Some earlier version of Siri use concatenative approach. And besides concatenative approach, another popular approach is parametrics approach. I'm not going to go through the detail here. There are some hidden Markov model here, and based on hidden Markov model, you can do the speech synthesis. And before end-to-end, people already start to try some deep learning-based approach, just like speech recognition. I say in speech recognition, there are some hybrid model. In the hybrid model, you have several modules, and some of the module is already deep learning based. In TTS, is exactly the same. There's a model called Deep Voice. It has several modules. It has graphing to phoneme. It has duration prediction module. It has fundamental prediction module. It has audio synthesis module. Don't worry about this module. They are just some module in the TTS system. And all the module here is already deep learning based. They just do not concatenate all the module and train it in an end-to-end way. So this is some model before the end-to-end. For end-to-end speech synthesis, the most popular model, I think, is Tacotron. But before we talk about Tacotron, there's something I need to talk about. So in speech synthesis, the input is text sequence. The output is acoustic features. Oh, I found that there is a question here. So let me try to read it. In the acoustic feature part, you mentioned that Google and Facebook use enormous amount of data. In general, how do NLP researchers rival those corporations that have monstrous amount of data and computation resources? This is a very good question. We usually have some problem to compete with those giant companies. However, if what you want to do is research, it is not necessary to really play on those very, very large models. Actually, even for the researchers in Google and Facebook, when they write a paper, they usually try their model on the benchmark corpus. So this is kind of fair comparison. Everyone use the benchmark corpus instead of using the very, very large data set that no one can really train it. We appreciate the result on the benchmark corpus. So you don't really have to play with the 100,000 of hours to publish some result. If you only want to do some research, libre speech is good enough. I hope this answers your question. Okay, so the input is text sequence, the output is acoustic feature. However, we cannot directly listen to those acoustic features. We need one thing called vocoder to transform the acoustic feature back to the waveform. Why we need a vocoder here? Why we cannot directly transform acoustic feature back to the waveform? This is because when we transform the waveform into acoustic feature, we lost some information. So this procedure is not irreversible. When you transform the waveform into acoustic feature, it is not trivial to transform the acoustic feature back to the waveform. Let's take spectrogram as our example. When you transform the waveform into spectrogram, you lose the information which is called phase. Don't worry if you do not know what is phase. Here I have some example to show what is lost when we transform the waveform into the spectrogram. The original waveform sounds like this.
This no longer appears to be the case.
And when we transform this waveform into the spectrogram, we lose some information. Then when we transform it back to the waveform, it sounds like this.
This no longer appears to be the case.
In general, you can still understand what the utterance is talk about. However, you know the quality is different. So phase is not really directly related to the content of the utterance. So when you transform the waveform into spectrogram and use spectrogram to do the speech recognition, you do not miss the important information. You do not miss the information about content. However, if you transform the spectrogram back to the waveform, there's some problem because there's some information missing, so the audio quality is degraded. So how to deal with this problem? We need a vocoder here. Vocoder take the acoustic feature as input and try to reconstruct the waveform from the acoustic feature. If your acoustic feature is spectrogram, waveform will try to recover the phase information. You try to put the phase information back into the spectrogram so you can generate high quality waveform. Vocoder can be raw based, But recently, people start to working on neural-based vocoder, and WebNet is a very good example for neural network-based vocoder. Here we have a question. Let me read the question. The question is, once the TTS model are trained using a large data set containing many speakers, it is easy to obtain my unique model using just a few my utterance. Unique model means it will output speech of my voice print. And how about the performance of the unique model sets? Well, this is a very good question. This kind of application, you can find lots of related paper in the speech conference. Actually, in ICAST 2021, there's a challenge exactly the same as what you are talking about. That is, you have to train a model, and for each target user, he or she only provide 5 authors, and your model have to be personalized based on the 5 authors. Actually, our lab also participated in that competition, and we are in the 2nd place. For the performance, in my point of view, I can still tell the difference between the synthesized speech and the original target speaker. However, I think the quality is already pretty good. If you have not listened to the target speaker, you will think the synthesized speech has high quality. However, if you have listened to the audio of target speaker, you can tell the difference. If you want to learn more about it, you can check the challenge in ICAST 2021. Okay, so here we have a question. Suppose that we have this sequence will come to NIS, and its corresponding speech. Is that make sense to consider its backward version as SIS or Imoku, and also, well, I'm sorry that this question is not finished again. Yeah, while we're waiting for people typing, we can probably tell you more about the end-to-end model. So I say Tacotron is the most well-known end-to-end TTS model. And why it is named Tacotron? The first author told me that it's originally named Tocotron, means it can talk. And Tron does not have any special meaning. Tron just want to make it sound like a robot. But then they finally decided to name it Tacotron. Taco is this kind of food. And they actually have a footnote in their paper say this author, some of the authors like tacos, and some of the authors prefer sushi. And Tacotron is just a sequence-to-sequence model. That's it. The sequence model take characters as input and output the spectrogram. Then with a vocoder, you can transform the spectrogram back to the waveform. That this is Tacotron. And Tacotron has very good performance. It's so good that before I tell you how good it is, here is some number. This number is mean opinion score. That is, you ask some human to evaluate your system, and they give the system score 1 to 5, and you compute the average. This is mean opinion score. In the first version of Tacotron, it's better than parametric-based approach, but it's not as good as the concatenative approach. However, in the second version, they do some modifications. So in the second version of Tacotron, it's outperform the parametric-based approach and also outperform the concatenative-based approach. And actually, it's very close to the ground truth. It's very close to the real speech. And its performance is so good that in the keynote speech of Takuda is a very well-known TTS researcher. He has working on TTS more than 30 years. In his keynote, he say, this is what he think when he listened to the audio of Tacotron. He recalled that in 1980s, there is a very famous word in speech technology. Frederick Janelic said every time he fired a linguistic, the performance of the speech recognition goes up. And when Takuda listened to the audio of Takotron, he kind of worried that he is useless. He said probably one day people will say, every time I fire a speech technology researcher, the performance of speech synthesizer goes up. Because with this kind of sequence-to-sequence model, probably we do not need speech technology researcher anymore. We just need to buy more machine, collect high quality data and train the model, and this is all you need. Is this true? Fortunately, or probably unfortunately, Takotron is not as good as expected. Here, I'm going to use Takotron to read its abstract. Then you can listen to it to tell me how good it is.
A text-to-speech synthesis system typically consists of multiple stages, such as a text analysis front-end, an acoustic model, and an audio synthesis module. Building these components often requires extensive domain expertise and may contain brittle design choices. A per B present Takotron, end-to-end generative text-to-speech
So you can find that
comparators.
in the first two sentences, Takotron performed pretty well. I know the audio quality doesn't sound perfect here. This is only because we do not have a perfect vocoder. In Google's paper, they have a very high quality vocoder, so the audio is almost perfect. You cannot hear that very little noise in the audio. However, when the model reads the third sentence, it's just a disaster. It did not complete the sentences. It tried to read Takotron, actually correctly read Takotron. Then it just say text to speech, then it just say character, then the sentence is finished. So it did not go through the third sentence at all. This is the problem of Takotron. Because it is an end-to-end model, you do not know what is happening in this end-to-end model. So if you let your Takotron read some very long sentences, probably longer than all the sentences in your training data, or if you make your Takotron read some very short sentence, shorter than most of your sentence in the training data, it will cause some problem. So you need to invent some new way to make the speech synthesis more stable. Let's see whether we have some question here. Okay, we do not have a new question here. So there's another model called fast speech. And fast speech, this proposed approach is just exactly the same as duration-informed attention network, or DURIN. So these two papers are published almost at the same time. So in fast speech or in DURIN, they deal with the end-to-end speech synthesized in this way. Input is character, output is spectrogram, and you have an encoder transform those characters into embedding. Then you have a duration model. Duration model try to predict the length of each character. Duration model is also a neural network. It takes the embedding here as input and output a number. And the length of the spectrogram, the length of the output will be determined by the output of your duration model. For example, if the duration model gives 2 to the first embedding, to the embedding of C, then you will duplicate the first embedding twice. And here we have duration 3. So the second embedding is duplicated 3 times. Here we have duration 1. Then we simply copy the embedding here. Because the total number of duration here, the total length of the duration here is 6. So the length of the output spectrogram will be 6. So this is the duplicated embedding. Then there's the decoder. The decoder takes this sequence as input. This is not a sequence-to-sequence model. Its input and output has exactly the same length. You take the embedding here, then it output the spectrogram with the same length. So this is fast speech and DURIN. So you can find that this is a rebirth of duration model. So we have a duration model here. in the tacotron, there's no duration model. It's just one gigantic network, which is end-to-end. But I have mentioned that before we have tacotron, the voice have several modules. One of the module is called duration module. Now people to put the duration model back into the end-to-end model. So why is this kind of duration model helpful? Because it is more interpretable. You know the duration of each embedding here. You know the duration of each character here. If you don't want your model to miss any character, you just force your duration model never output 0. So if your duration model always gives some length to each character, then all the character will be read. But there's a problem here. Here, the output of the duration model is an integer. Then how can we train this model end-to-end? Different from the previous concatenated model, different from the first version of deep voice, the fast speech or during, all the module here are trained end-to-end. So it is still considered as an end-to-end module. It just has a duration model, which is interpretable. So how to train this end-to-end model? We do not have time to go through it here. You can check the original paper for more details. So here is the result from the original paper of fast speech. They ask tacotron 2 and transformer TTS. Just use transformer as your end-to-end TTS model. They ask those models to read some very difficult sentences. There are some random numbers or some URL, and it is very hard for tacotron to read those sentences completely correct. But fast speech is correct on all this kind of sentences. And besides just input text and output speech, we need another research direction is controllable TTS. We do not have time to go through controllable TTS. Today, you can say, besides given the text as the input of TTS, you can also provide it speaker information and emotion information. So you can make your TTS sound like a specific speaker, or you can control the expression of your TTS model. To learn more about TTS, probably you can check the survey paper below. Okay. So we have more questions here. Why isn't the passage for tacotron broken down into sentences? I think there can be some upper limit for how long a single sentence can be. Yes, you can break down the sentence based on, you can break down the passage based on the sentences. However, tacotron, it can read punctuation. So even though you give a whole passage, it can try to read it. But I just want to show that sometimes tacotron can make mistake. Even though you do not give it a whole passage, you can still find some example that tacotron miss some character or miss some words in the whole sentence. Here's another question. May I have a question, please? Is there overfitting in speech processing? How does it look like and how to solve with this problem? Of course, there is overfitting. So I just demonstrated that if you give tacotron very long sentence, much longer than most of the sentences in this training data, it cannot read the sentence correctly. This is a very typical example of overfitting. It overfit on the length of the sentence it has seen before. Actually, if you provide tacotron very short sentence, sometimes it will also have the problem. Not only the long sentence causes the problem, short sentence can also cause the problem because this is out of distribution sentences. Oh, suppose some words do not exist in the dataset. Can the model synthesize the audio for those words? Yes. So you can find that actually the input of those end-to-end TTS model can be character. So even though some of the word never appear in the sentences, the model will still try to read it. For example, in the example of tacotron, you found that it almost correctly pronounced the word tacotron. I believe the word tacotron is a new word for the model. I believe the word is not exist in the training data, but Taco Trump correctly read the word. So even though there's some out of vocabulary word, even some word not in the training data, the TTS model, those kind of end-to-end TTS model, have very high possibility that it can read it. How about the accent the speaker used, like American or British English? Yeah, the essence of the TTS model is based on the training data you provided. So you provide which kind of training data, it just sounds like the training data you provided. If you want your TTS model to have different kind of accent, you have to collect the data with different kind of accent. So you want it has British English accent, then you have to train your model with British English. I hope, do I answer all the questions? Okay, yes. Okay, we have around 20 minutes before the end of the lecture. So I still have two topics I want to share with you. One topic is speech separation. So in speech separation model, the input is speech signal, the output is also speech signal. So what is speech separation? In speech separation, your model have to separate the speech we care about from the background noise or the speech of other people. Actually, human can do that easily. As you know, human can focus on the voice produced by a single speaker in a crowded and noisy environment. And this is called cocktail party effect. Can the model do the same thing? There are two types of speech separation. One type of speech separation is to separate speech and non-speech. You need to separate the speech from the background noise. This is called speech enhancement or denoising. What I want to focus on today is speaker separation. That is, multiple speakers talking at the same time, and the model, the input of the model is the mixture of the audio or the speaker talking at the same time. Can your model separate the audio, the speech, the voice of each speaker? In general, the speaker separation model is like this. The input is mixed audio, and the output is two utterance. The output is the separated utterance. The input is an utterance, but it includes mixed audio, and the output is two separated utterance. Here we focus on the case that in the mixed audio, there are only two speakers, but it is pretty easy to generalize to more sophisticated cases. And we only focus on single microphone. That is, we only have one microphone. It would be easier to do speaker separation with multiple microphones. So we only consider one microphone here, which is a more challenging task. And we consider speaker independent condition. That is, the training speaker and the testing speaker are completely different. Your speaker separation model trained on a set of speakers, and we want to know that whether it can generalize to new speaker. Then what is this speaker separation model looks like? To make the long story short, you can just imagine that it's a sequence-to-sequence model with two decoders. So input mixed audio and encoder encode the mixed audio. Then you have decoder 1, which output the red utterance here, and you have decoder 2, which output the blue utterance here. And it's relatively easy to collect training data for speech separation because you only have to take two utterance and mix them together. Then you have the input of the model and the ground truth of your model. However, to train a speaker separation model, there's an issue called permutation issue. The issue is like this. We know that the input of the speaker model is this, and the output ground truth should be the blue utterance and the red utterance. However, should we let the first decoder output the red utterance, or should we let it output the blue utterance? Should the second decoder output blue utterance, or it should output the red utterance? We do not know. Probably you would think this is not a big deal. Just randomly assign it. Just randomly say red utterance is the output of the first decoder, and blue utterance is the output of the second decoder. Just randomly choose one of the possibilities. However, this will not solve the problem. You can consider if we have two training examples. The first example is we mix the blue one and the red one, and the second example is we mix the blue one and the red one, and the second example is we mix the green one and the yellow one. Okay. In this case, let's assume that the blue one is male speaker, and the red one is female, green one is female, and the yellow one is male. Then let's say you random assign the output, you random assign the ground truth of your speaker separation. You say the red one is the output of the decoder one, and the yellow one is also the output of decoder one. However, the red one is female's voice. The yellow one is male's voice. So for the speech separation, for the decoder one, it will be very confused because sometimes, because the input is both male plus female, however, sometimes you ask first decoder to output female's voice, and sometimes you ask it to output male's voice, then your decoder will be confused. Actually, in the real implementation, if you random assign the ground truth, then you cannot successfully train your speaker separation model. It will not converge. To deal with this problem, probably we have to cluster those utterances. For example, probably we can say the first decoder output the utterance with larger energy, and the second decoder always output the utterance with smaller energy. Will it work? It works a little bit. This is the result if you use energy to assign the ground truth. The vertical axis is SDRI. Don't worry about SDRI. It's just one measure for source separation. The larger the value means better the separation result. So you get 14 here. Actually, this is a pretty good number, but you can tell that there are other approaches which can get better result. How about cluster by speaker characteristic? So you separate your speaker into two groups. The speaker belong to group 1 will be the output of decoder 1. The speaker belong to group 2 will be output of the decoder 2. Will it work? It is better than the energy, but there are other approaches that can achieve better performance. I found that there are some questions. Let me try to answer that. Would then incorporating a learnable model of a physical voice production system, vocal cords, vocal tract, be an invaluable induction bias as a submodule of a TTS system, instead of just blindly trying to learn the production model end-to-end and without leveraging any bias from physics of voice production? Well, this is a very good idea. I have to say this is a good idea. I do not find too much paper working on that. Today, most of the paper, they are based on an end-to-end model. But if you have a lot of knowledge about the voice production, I encourage you to try to put those kind of inductive bias back to today's end-to-end model to see whether you can get better performance. This will be a good research direction. Oh, someone asked how to solve the task of mixture language condition, like Chinese with some English pronounce some English professional words. This is a very good question. This situation is called code switching in the literature. So in speech recognition or in synthesis, code switching is a very good research topic. In the speech conference, there will be a whole session or even a whole workshop discuss this topic. So the major issue of code switching is it is difficult to collect sufficient data. Usually you have lots of English data, you have lots of pure Chinese data, but you cannot collect too much code switching data. So how to train your model from mono language, then adaptive with just a very little bit code switching data will be a very good research topic. And there are many different ways to achieve that. For example, our lab have proposed some approach, try to use data augmentation technique to generate more data to train code switching, and it is kind of helpful. But there's lots of different directions you can research on based on the code switching topic. Oh, here is a question. Is it possible that sometimes both the decoder output the same audio? Okay, this is a very good question. During the training time, I know you mean we input the mixture of audio. We'll probably let the speaker separation model only extract one alternate. It ignores the other one and only extract one alternate from both decoder. During the training time, because the ground truth of these two decoder are different, so this is not so. Hopefully, speaker separation model will not learn to do that. However, in reality, in the real implementation, when you train on some domain and test it on some very different domain, you have overfitting issue. It is possible that your speaker separation model is completely failed. So both the decoder output exactly the same thing, but this will be considered as an error. This can happen if the overfitting happens. Okay, I hope I answer all the questions. Do I miss something? Okay, here we have a question I missed. Can the problem of permutation be solved by using all possible permutation as labels? The answer is no. You can try that, but I believe it will not work, because if you say, if you put all the permutation as the output, then you ask your decoder to output two different signals. Given the same input mixture, you have to output two to deal with this problem. This is called permutation invariant training. So in permutation invariant training, or PIT, you need an initialized speaker separation model. And you use this initialized speaker separation model to determine the permutation. So you already have a speaker separation model, and you try each permutation to see which permutation obtain the smaller loss. Then you choose the permutation with the smaller loss to train your model. However, this is a chicken and egg problem, because we do not have the speaker separation model at the very beginning. So how to do permutation invariant training? Actually, it works in this way. You have a random initialized model. You use the random initialized model to first get the permutation. Then you use the permutation to train the model. Then you have a new model, so you can do the new permutation again. And then you just do the permutation and the model training iteratively. So this is the basic idea of PIT. There's no theoretically guarantee that this process will converge in the end, but in real implementation, it usually converges. So you can find that. So this blue curve represents the percentage of switch during the permutation assignment. You can find that at the first few epochs of training, the permutation assignment changed very fast, but it converged in the end. So PIT worked better than the other two approaches. Then why is this one? We do not have time to go through it. You can check the paper yourself. So here is the result of speech separation, speaker separation based on an end-to-end model. The most well-known end-to-end model for speaker separation is TestNet, Time Domain Audio Separation Network. And actually, it is not a sequence-to-sequence model. it is not a sequence-to-sequence model with 2 decoders. So this is another example about the domain knowledge is very important. I do not have time to tell you why it is designed in this way. This is based on some domain knowledge. So actually, it do not have 2 decoders. It output 2 masks, and it used 2 masks and 1 decoder to generate the separated audio. But anyway, it is still an end-to-end model. You still need to train by permutation invariant training. Then, how's its performance? Here is the demonstration. This is the input audio.
The female produces a litter of 2 to 4 young in November in
Two females speak simultaneously, and this is the separation result.
When its initial public offering is completed, Ashland. The female produces a litter of 2 to 4 young in November and December.
Can achieve pretty good performance on the benchmark corpus. This is more speaker separation model. So let's see whether we have some question in the chat room. Okay, no. Okay, this is the last part of this lecture. In the last part, I'm going to talk about voice conversion. In the voice conversion model, the input is speech signal, the output is also speech signal. However, there is some difference between the input and output. We need to preserve something and modify something. What we need to preserve here, usually in voice conversion, what is preserved is the content. And you can change different attributes in speech. For example, you can change the speaker identity. I believe change the speaker identity is not something new for you because Conan, in Detective Conan, there is a voice changing bow tie, which can do voice conversion very successfully, which can change speaker identification very successfully. It looks like Agassi Hiroshi already proposed very good approach about voice conversion 20 years before. So this is about change the speaker identity. There's also other stuff, other attribute that can be modified. For example, you can modify the emotion in the utterance. You can change the utterance from normal to lomba. Lomba is one way, is one kind of speaking style. We do not have time to go through that. You can change from whisper to normal, and you can even change the singer's vocal technique. Okay. And there's other application about voice conversion. Voice conversion can also be used to improve the intelligibility. In Taiwan, oral cancer is one very serious cancer. It's top 5 cancer for male in Taiwan. And the surgical patient who had part of their articulator removed, they cannot alter the utterance intelligible. To make their voice more intelligible, probably you can use voice conversion to change the unintelligible voice into intelligible voice. So this is another application of voice conversion. Besides that, voice conversion also used in data augmentation. Some people will use voice conversion technique to increase the number of your training data in speech recognition. For example, you can convert the voice of all the male into female or the female into male, then you have twice the amount of training data. And there are 2 categories of voice conversion. One is if we have parallel data, then training a voice conversion model is not an issue. If you can collect large enough pair data, if you can collect sufficient number of pair data, then you can use those pair data to train a sequence-to-sequence model in the conventional way. Then the problem of voice conversion is solved. However, to collect a large parallel data is probably impractical. So in the community of voice conversion, most of the research effort is focused on how to leverage unparalleled data to train a voice conversion model. For example, you have one speaker which speaks Mandarin Chinese, another speaker speaks English. You have some audio, you have some voice of speaker 1, and you have some voice of speaker too. However, they are not parallel. They are talking about completely different thing, or they are even in different languages. Can we train a voice conversion model in this way? Can we train a voice conversion model without any air data? So the basic idea is based on feature disentangle. Actually, there are many different ways to achieve voice conversion, but what I want to share with you today is feature disentangle. So what do we do in feature disentangle? As I have mentioned in speech, there are different attributes, include content, include speaker identity, and other information, for example, prosody. Can we have the encoder to extract different attributes from the utterance? Can we have a content encoder that extract the content from the audio, and speaker encoder that extract the speaker identity, that extract the speaker characteristic from the audio? If we can do that, then with a decoder, which take the output of content encoder as input and speaker encoder as input, it can synthesize the original audio. And we can achieve feature disentangle in this way. We can separate the content information and the speaker information. I found that there's a question in the chat room. Let me read the question. If even permutation is a problem, it will not converge. Is the test of separation and unknown number speaker too soon to be tackled? First of all, I have to say that in permutation invariant training, I just say theoretically, there's no guarantee that it will converge, but practically, based on my experience, empirically, it always converge. And for unknown number of speaker, there's already tons of paper trying to tackle this problem. So how to tackle this problem? There are different ways. One way is you have a speaker separation model, and it has a large number of different decoders. For example, if you know that the number of speaker is always less than, let's say 5, then you just have 5 decoders. If the number of the speaker is less than 5, then only some of the decoder will output voice. So this is one way. Another way is apply a source separation model, apply a speaker separation model iteratively. You have a speaker separation model which can always extract the voice of one speaker from the mixture. So let's say you have 5 speakers in the mixture, then your model will extract the first one, then you apply the same model again, then you extract another one, then you apply the model 5 times, then you extract all the 5 speakers in the mixture. So this is another way to tackle the problem with unknown number of speakers. About speech intelligibility, may you combine this problem with the previous mentioned modeling how speech is produced to solve it, since both seem to be strongly related to articulatory. This is a very good idea, but I have to mention that for the paper I cited, they are just end-to-end. For example, in the paper, so I cited 2 papers. One is from my group, another one is from Google. And in Google's paper, they are just use a transformer, a sequence-to-sequence model to make the speech more intelligible. So I think put the domain knowledge or kind of voice production model into those end-to-end model will be a good research direction. But I do not see many successful examples at this stage. But I believe this will be a good research direction. Okay, so what I have said. Okay, so now we have content encoder, speaker encoder, and we have a decoder. Then to do voice conversion, what you have to do is use the content encoder to extract the content of this male speaker. Then here we have a female speaker. Actually, she's not a random people. She's Yui, but don't worry if you do not know who she is. She's a very famous Japanese actress. this is the voice of Yui, and you extract the speaker characteristic of her. Then you concatenate these two representations together, and your decoder synthesizes the voice. Then you can use Yui's voice to read the sentence of this male speaker. Actually, this is me. Then you can, if you have the content encoder, speaker encoder, and decoder, you can achieve voice conversion in this way. Then the problem is how to train the content encoder and the speaker encoder. During the training time, what you really do is like this. You train an autoencoder, input and audio, and you have to reconstruct exactly the same signal. And you jointly train this content encoder, speaker encoder, and the decoder. However, if these two encoder and the decoder, they are jointly trained, how can we achieve feature disentangle? How can we make this encoder encode content and this yellow encoder encode speaker? How can we make these two encoder encode different information? And this is what is interesting in the feature disentangle. This is the core research problem in voice conversion. And there are several ways to achieve it. The most widely used approach, and if you have seen any demo about voice conversion, usually they use this approach because this is the most stable one, is you have a good pre-training encoder. For example, for speaker encoder, there are tons of different ways to pre-train this speaker encoder. There are many different ways to have a model which given an utterance which can output the speaker embedding, which can output the speaker characteristic. One of the most representative model is AutoVC. For content encoder, you can initialize it by the encoder of speech recognition model, because speech recognition model is to extract the content information. So initialize this content encoder by speech recognition model will be a good idea. Usually this approach works pretty well. But the problem is, because we need a speech recognition model here, so this idea can only be applied on the language you already have a high quality speech recognition model. For the language, you do not have a speech recognition model, or for the language, you do not have writing system, you cannot apply this approach. There are other approaches that do not need a speech recognition model. One is based on adversarial training. Due to time limitation, I would like to skip this one. The last part, which is the third approach, which I found very interesting, is you can even design the network architecture to achieve speaker disentangle. So this is the place you need some domain knowledge. You need to know how to design your network architecture so you can remove the speaker information and preserve the content information. And we found that instant normalization is the operation which can remove the speaker information. This is how you do instant normalization. So this is the input signal, and you obtain the representation for each audio segment. Then you do a normalization here. The normalization is to make each channel has zero mean and univariance. And this kind of normalization can remove the speaker information from the utterance, because this is a global normalization among the whole utterance, and the speaker information is something globally in the whole utterance. So this kind of global normalization can successfully remove the speaker information. So due to time limitation, I would like to skip this part. The take-home message here is there's some way to design your network architecture to remove the speaker information or preserve the speaker information. So I just want to tell you that if you have some domain knowledge about the problem, you can even design your network architecture to achieve speaker disentangle. And in the last part of this talk, I would like to do some demonstration about how well this approach can be. So in this example, we have a content encoder, we have a speaker encoder, we have the decoder. During the training time, we do not do any pre-training. We just use the network architecture to make it disentangle different information.
Do you want to study a PhD?
So this is the input of the content encoder.
Do you want to study a PhD?
This is my voice. Say, do you want to study PhD? Because in Taiwan, little student want to study PhD, so a professor usually have to ask student to study PhD. And this is the input of speaker encoder. So this is the voice of Yui, and I'm not sure what she's talking about. Then content encoder will extract the content by voice, and speaker encoder will extract the speaker characteristic from Yui's voice, then put it together. This is what we have.
You want to study PhD?
So Yui used her voice to ask whether you want to study PhD. And we can do it in a reverse way. Content encoder extract what Yui said. This is Japanese. Actually, during the training time, content encoder have never listened to Japanese. And this is speaker encoder.
Do you want to study PhD?
My speaker characteristic, then put my speaker characteristic with what Yui say, then you can let me speak Japanese. I'm not sure what I'm talking about. So this is a survey paper about the robustness of voice conversion. We do not have time to go through that. So this is all I want to share with you today. So if you think, so this is one slide for this course. So if you do not remember other part, it's fine. Just keep in mind that we have 3 types of model. And in general, you can use sequence-to-sequence model to solve all the problems. I hope I convince you that if you are familiar with sequence-to-sequence, you are ready to engage in speech technology. And I hope I also convince you that to be the top in the field, sometimes you need to understand more than sequence-to-sequence. So this is today's talk. Thank you very much. And let me answer all your questions. It looks like my connection is kind of unstable. It's fine. Let me check whether there's some new question. No? Oh yes. No, I think there's no new question. We can wait for a few minutes to see whether the audience have any other question. So if you have any question, feel free to type in the chat room. I will see the question. If not, I know there's some question I did not really answer it because there's some question which is not finished during the typing. So if you still want, but even though it's already 10 minutes after 11 o'clock, but if you still have any question, feel free to leave your question in the chat room. Okay, okay. There is some question. Okay, how long do you think end-to-end model can surpass hybrid model? This is a very good question. In the paper, however, the performance of this 2 model depends on how many data you have. If you have only 100 hours of data and you are not targeted at published paper, you just want to build a commercial system, then I highly recommend you use hybrid model. If you have 100,000 of hours of data like Google, then I think you can try end-to-end model. Oh, a student asked, do you have any course about speech processing? Thanks. Oh, I have a YouTube channel, and on the YouTube channel, you can find the lecture about human language processing, include speech processing and natural language processing. But unfortunately, it's in Mandarin. I hope this is still useful for if you are Mandarin speakers. So let me check whether there are more questions. What do the future holds with regard to speech processing? Sorry that I do not really get this question. What do the future hold with regard to speech processing? So probably you can rephrase your question if possible. Any existing voice ID system deployed in production? Oh, you mean there's any commercial voice ID system deployed in production? There are several, actually several banks. For example, Citibank, they have voice identification system. When you call Citibank, they will have a voice identification system, check whether you are the customer. And there are also other banks, they also already have the same service. Here's a long question. The bulk of acoustic models in audio NL system rely on CNN architecture by treating the log mail representation as images. This is where CNN for vision are successful due to the spatial continuity inductive bias. This assumption does not hold for spectral dimension that is harmonic, but also long time dimension, alarm sounds. So why are CNN still used as acoustic model, and why are they successful? Actually, okay, this is a good question. So as you know, CNN usually used in the first layer of speech signal processing, usually used in the first layer of the encoder of speech recognition system. So why CNN is useful? So as you know, CNN tried to detect the repeated pattern in the images. Does this kind of repeated pattern appear in the spectrogram? Let me give you a very easy, simple example. So you can consider that when the male, as you know, male and female speaker, they have different pitch, right? So female speaker has higher pitch. However, when male and female speaker, they pronounce the same phoneme, the pattern looks similar, but they have different frequency. So if this is your spectrogram, when a male speak something, say something, probably the pattern set here. And if female say the same thing, the pattern will shift. And the same pattern can appear in different regions of the spectrogram. And this is what CNN can be helpful to detect this kind of repeated patterns. I hope this gives you an example why CNN may work in speech processing. In what extent different languages affect the performance of end-to-end model? This is a good question. I also do not have an answer. I really want to know this answer because today, all the languages, end-to-end model are widely used in many different languages. Can we know whether there are some languages intrinsically more difficult than other languages? But no one have tried to do that. Probably because there's no good way to compare between different languages. But this will be a very interesting topic, but I do not have any answer at this moment. I hope I answer most of your question. I can check the chat room myself to see whether I missed anything. Yeah, if you think I missed your question, because the question coming in pretty fast, so it is very easy to miss some of them. But if you think I missed anyone, you can let me know. You can type your question again. Here's a question: how well is speech combined with other modality? Okay, so this depends on your application, right? What kind of situation will you combine speech with image? Probably because you want to detect the lip shape to enhance the performance of speech recognition. Does this helpful? It is helpful in case that it is very noisy. So when you want to recognize the speech in the case that it is very noisy, detect the lip shape will be helpful. So I hope this answers your question. So, okay, any question from the audience? If you think I missed your question, you can type it again. I can see it immediately. Or if not, should we call it a day? Okay, if you do not have further questions, so this is the end of this lecture, and see you tomorrow. Bye-bye.